CTO of iSpace. Then from this part, I'm going to explain what happened at the really last moment of our landing sequence. Then, before, the explaining the cause, first of all, let me play back our planned orbit sequence. Then please move on next slide. Then, from this slide, I'm going to explain the sequence with animation. Please move back. Sorry, now phase 2. Okay. Yes, phase 1. Yes, its first phase is the orbit insertion, the maneuver. Then, before starting landing sequence, the lander is at 100 kilometer circular orbit. But after this DOI, the lander changed the orbit and then, target it to 100 kilometer by 20 kilometer elliptical orbit. Then please move on next slide. On the phase 2, lander was already on the course of the elliptical orbit. Then the lander was approaching to around 20 kilometer altitude. Then please move on next slide. But before that, at around 25 kilometer altitude, lander started the deacceleration operation. This is called braking ban. Then during that phase, the lander drastically decreased the velocity of it. Then please move on next slide. But in the phase 4, the lander started pitch up operation because the lander needed to the softly land on the moon. Then in order to vertically land on the moon, the lander need to change the attitude. Then such kind of pitch up operation they are executed in this phase 4. Then please move on next slide. And finally, phase 5, still the lander decrease the speed. Then with a vertical position, the lander is going to lander was approaching to the lunar surface. And at the really end of this phase, lander finally turned off the main engine. The main engine is 400 Newton thruster because it could disturb the lander control due to the reflection from the lunar surface. Then you take that into account, we turned off the 400 Newton thruster at the last moment. Then please move on next slide. Then final phase is phase 6. Then with really low speed, finally the lander was expected to softly touch down on the lunar surface. This was our original sequence. Then please move on the next slide. Then with this table, I'm going to explain what happened in the landing sequence indeed. As Takeshi explained, unfortunately, we could not complete our soft landing, and then finally lander reached that hard landing. Then with this table, I'm going to explain our understanding. Then here, about this table, we have 2 columns. One is the real-time telemetry event sequence. This table means what we saw the landing date by telemetry monitoring. Then in addition, today we added another column that is an event from post-flight analysis, telemetry analysis. Then by combining 2 columns, I'm going to explain what happened at the last moment. Then as I explained, number 1, the phase 1, DOI start, that was expected. And in the phase 2, during the cruise, the occultation period was successfully ended. That means the communication restarted. The timing was also expected range. At that moment, we were confident in the successful DOI. Then after that, the number 3, the braking ban was also successfully started. That was also really expected timing. That was great. And in addition, number 4, this is quite important. At that moment, even in our mission control center, we confirmed estimated altitude update by laser rangefinder measurement. Here, estimated altitude means the landers, lander has a software, and that software always estimate the altitude, position. Then, this estimated altitude means, the lander estimated altitude. In addition, lander has a laser rangefinder. That this is a sensor to measure the altitude. Then, with this laser rangefinder, lander always correct this estimated altitude and then improve this estimation. Then this correction successfully happened at number 4. Then even after post-flight analysis, we also confirmed multiple measurement update, as you see in the 5, 6, 7. However, in the post-flight analysis, we also realized the huge gap between estimated and measured altitude. That gap was more than 3 kilometers, the altitude. But in the real-time monitoring, we did not realize that. Then, at number 9, Lambda successfully started the pitch up operation. Then Lambda was, successfully in the vertical position. Then the number 10, Lambda finally in the terminal descent, and then number 11, we also confirmed, the indication of estimated altitude 0. That means at the moment we really expected touchdown happen, but indeed it did not happen, unfortunately. Then even after that, Lambda kept, descending, and then we also confirmed the altitude, was negative. However, in the right-hand side column, in reality, with the post-flight analysis, we also confirmed the expected touchdown moment. I mean, the timing estimated altitude was 0. I mean, number 11, measurement altitude indicated 5 kilometers. Then that means, the Lambda expected, on the lunar surface at this point. However, in reality, that is from, apart from 5 kilometers from the lunar surface. Then, but the Lambda kept descending, but finally, Lambda ran out all propellant. We also confirmed that indication with tank pressure monitoring. And then finally, free fall started, and then, reached that loss of the communication. This is the event sequence of that landing day. Then please move on next slide. Then yes, this is equivalent to the previous table. Then here the important point is the right hand side the figure at number 8. At that timing, we confirmed huge gap between estimated altitude and measured altitude. That means here the right hand vertical axis is estimated altitude. And then right-hand vertical axis is measured altitude. As you see, at number 8 timing, you can identify the 3 kilometer gap. Then here, the question is why this gap happened. Then please move on next slide. Then, this is the actual flight data plot. Then, the blue line is estimated altitude, and the red line is measured altitude. Then here, when we start measurement, I mean the start point of the red line, the blue line has also really relatively large jump. This large jump means successfully onboard software of the Lambda, the reflected measurement result into the estimate altitude and correct the altitude. Then after that, as you see here, both blue and red line, are gradually converged. This is also really good sign. That means now estimation and measurement were almost consistent. That is a good sign. However, after that, as you see in this graph, suddenly red line, increase. Then, even after that, we have an additional, increase in the red line. Then finally, the gap reached at 3 kilometers. Then both red and blue line never converged. That was, the flight data, the analysis result. Then here, the further investigation was required. Why this gap started? Then please move on next slide. Then here, this is, the map data. Then, in the center picture, you can identify the white line. This white line is our planned trajectory. And then the black circle is our target, the landing area. Then, the red point is the, the estimated hard landing point based on NASA LRO the measurement result. By the way, that NASA LRO picture, what's in the right-hand side picture. Then please move on next slide. Then here, this is like a 3D map, of the trajectory and terrain information. Then here again, the white line is a projection of our the landing trajectory. Then here our lander, fly over the rim of the crater. Then at the rim, you can identify really steep altitude change. Then this steep altitude change, corresponded to the gap, the initiation timing. Then that means that gap between estimated altitude and measured altitude was due to this crater rim. Then please move on next slide. Yes, here, yes, as I already explained, this is the cause of the continuous descent without measurement update was the crater rim, and our software design was not capable of correctly reflecting that data and then corrected estimated altitude. Then the point is here, yes, sensor seems to output correct data, and then because sensor correctly captured that crater rim changes. Then, but here the important point is this function, this filtering function. Filtering function means the function to discard measured altitude data greatly deviated from the estimated altitude is our intention, is our design feature, to make our control system more robust, robust against like a sensor hardware failure and so on. Then this design itself was our intention. Then but this was the design intention. But the point is we could not correctly reflect the lunar terrain and topological information into our detailed software tuning setting. Then due to this, insufficient, how can I say, parameter setting, finally, lander software could not correctly recognize the crater rim, and then the huge gap happened. Then here, if when we discuss more, deeply about the cause of this issue, we have to say, that change of target landing site impacted on this, failure finally. Then the point is, yes, we have an original, target landing site, but by considering, all benefit for our lander and payload, we changed the target landing site before CDR. Then due to this change, we had it impact on our development activity. Of course, we carried out a lot of simulation, a lot of test campaign. However, due to this change, we could not, correctly identify the issue before landing date. Yeah, then please move on next slide. Yes, then here in this slide, I would like to share our improvement run. Yes, first of all, surely in the software perspective, we need a fine-tuning of detailed lander software design. Then in addition, yes, if we correctly carried out the simulation by considering terrain or topological data, yes, we could identify the issue in advance. Then improved terrain simulation, range setting, and test campaign, of course, should be required. And then in addition, the radar velocimeter. Today, we didn't mention the radar velocimeter very much, but due to that, the gap between measurement and estimated altitude, the lander just started the free fall from 5 kilometers. However, this radar velocimeter range was, from 2 kilometer altitude. That means in this, the mission, unfortunately, we could not prove the radar velocimeter. Then, of course, we already completed, tested on the ground. But the more important point is we need to more ensure the performance of radar velocimeter. Then, now we are planning additional radar velocimeter field test on the ground to, get more confident in our radar velocimeter performance. Then, finally, the most important point is the early determination of the landing site. Because again, the last change of landing site, impacted on this issue. Then the important lessons learned is we should, determine the landing site area, and then should be kept, the proper duration for, the verification and validation activity for our landing sequence. Then on the other hand, the impact on the schedule and cost, we didn't identify any major impact. Then all, the modification or improvement can be done by the end of current fiscal year. I mean, the end of March 2024. Then again, these activity are, not major change. Then, it is almost as part of our planned process. Then, within the current, the schedule and cost, we are going to complete all improvement. Yeah, then please move on. Next slide. Then here I described in more detailed, how can I say, the gain in each subsystem. Then I won't explain, each item one by one. But let me, give some example. For example, in the communication side, our lander, reached out 1.4 mega kilometer from the Earth. Then even at that farthest point, we verified our own communication performance. And then, because this is a lunar mission, then lander reached out to lunar, the gravity region and lunar orbit. Then at that timing, we also expected some disturbance on the communication due to the moon. Then, in our flight, we also confirmed how much disturbance actually happened. Then that such kind of data should, surely improve our future mission and even the mission 2 or mission 3 too. Then like that, each subsystem has a lot of feedback, from this mission 1 to future mission. Then based on this lesson learned, we are going to keep improving our future mission. Please move on next slide. Then finally, let me, introduce the data, the picture, taken during our mission 1. Then this is also really important achievement for us. Then the first is, like a short movie of the Earth sunrise timing. Then, I know, a few government space agency already took this type of movie or picture before. However, we iSpace are commercial company, but even now, even commercial company can realize this type of really impressive lunar movie. And please move on next slide. Then yes, this is another movie from 100 kilometer altitude. And this is also really impressive. The lunar surface looks like a really close. Then you can identify really detailed terrain, the features on the lunar surface. Then please move on next slide. Then this is like a Earth, the Earth setting moment. Now Earth is approaching to the lunar horizon. Then this is also really impressive, the picture too. Then please move on next slide. Then yes, this is really, personally, this is really impressive picture because this is the first picture of the moon taken by ourselves. Then, this is a bit far from the other pictures. However, and then, the moon is not at the center of the picture. However, this moon is really impressive for iSpace. Then please move on next slide. But the most important achievement in this mission, I would say the team. After the landing date, I sent a message to all the engineers. Great challenge makes great team. That means this great challenge, commercial lunar landing, made a great team. Then I believe this great team, makes a great achievement, successful lunar landing in the next mission. Thank you very much.
Thank you, Ryo. So before going to the Q&A, let me add several other points other than the technical perspective. Going to the next. Yep. And then, regarding the interaction communication with customers, we have been conducting the explanation of the detailed analysis of landing sequence to the each of customer like today. And then mission 1 is to be officially declared concluded based on the confirmation with each of customers to the final report. And we have been obtained a lot of the flight data, and then until success 8 and almost success 9. And this data will be provided to the customer based on the individual contract. And then further, we have been discussing concerning individually how to utilize this data to the future missions with customers. And then next is the impact to the financial side. As we provided expected financial impact the couple of weeks ago during the financial report, the brief, the situation hasn't been changed even after the detailed analysis of the mission 1 result. The first, the impact of the sales. Even though there's a small changes, decrease of the sales from the mission 1 about 100 million Japanese yen. However, this impact is not significant. So toward the fiscal year ending March 24 result. So we will have no change of the forecast. And then also we don't have any impact to the sales contract already contracted for the mission 2 and the mission 3. And then we don't expect any major changes for the outlook of the future orders of the mission 2 and the further missions. In the aspect of the cost side as well, Ryo explained briefly, we don't expect any increase of the cost significantly. So we don't have any change of the cost for the mission 2 and then mission 3 due to this failure of the mission 1. And then impact of the schedule of the future missions, we don't have any expectation, we don't have any plan to change mission 2 and the mission 3 due to this mission 1 failure. So we're gonna plan to launch as scheduled 24 for second mission and then 25 for the third mission. And then other than these things, where we have lunar insurance, contracted with the Mitsui Sumitomo Insurance Company, and then we are still expecting to receive the insurance payment. However, it is not have been confirmed at this point. And then so the amount of the insurance payment is not reflected in the forecast of the fiscal year ending March 24. And then let me again emphasize here sustainable business model. In this space business, it's important to keep the sustainability of the business. In order to achieve that, we've already started 3 missions development simultaneously. And then now we almost finished the mission 1, having the final analysis of the result. And then now we are going to feedback lesson learned to mission 2 and the mission 3 immediately. And then in order to sustain these 3 multiple mission development, we've have been raising a large amount of money from the capital raising, bank loan, and then from the customers' advanced sales. And then we have a great basis of the financial background. With this background, we continue to develop Mission 2 and Mission 3 as we planned. And then, so as we explained today, Mission 1 demonstrated a great deal of technical capability as we landed reached to the lunar surface just prior to just a landing touchdown on the moon. Now we have been able to identify issue during the landing, and then we have a very clear picture of how to improve our future missions. While it is unfortunate that we are not able to fully meet the expectations from all the stakeholders in the world, however, all of us at iSpace are very positive already, and we are very proud of what we have accomplished so far. I appreciate very much for our stakeholders, including our customers, our partners, and the shareholders, allow us to keep this challenge, believing in iSpace vision. On return, in order to keep your trust to us, I'd like to keep this transparency like today. We have already begun work on Mission 2 and the Mission 3. We are prepared to face challenges and make every effort to improve. We will ensure that the valuable knowledge gained from Mission 1 will lead us to the next stage of evolution. We believe that this is our commitment and our duty to all our stakeholders. Never quit the lunar quest. In this spirit, we will continue to move forward. Thank you very much. And then now we are moving to Q&A.
Thank you, everyone. We'll move into the Q&A session now. We ask that you identify yourself by name and organization on your Zoom ID. Please use the raise hand function to ask a question, and we will call on participants in order. First question will go to Marcia Dunn.
Hello, can you hear me?
Yeah.
Yes, wonderful. Thank you for this briefing. I want to make sure I understand that you changed the location of the lunar landing site. When did that change take place and why? And so was that one of the main contributors to the accident, do you think?
Okay, yes, thank you for your question. Then let me explain the landing site change. Unfortunately, now I cannot disclose the specific date, to change, that landing site. But again, that change happened, the CDR, after CDR, critical design review. And I think company officially announced the completion of CDR, I think 2021 February. I think. Then, I think we also announced that current target landing site is 2022 November, I think. Then between that, I'm sorry, it's really, really big. However, between that moment, we changed our landing site. Then, for the reason why we changed the landing site is to maximize the benefit of the mission. Here, in this context, the benefit of mission means maximize the benefit of lander side and customer payload side. By considering all benefit, we tried to maximize the benefit, of course, within our original requirement for performance. Then, however, that decision, happened after CDR. Then, of course, we did a lot of, the simulation even after the landing site change. But of course, but however, due to that, we could not, identify the cause, the issue of the crater rim. the before landing date.
So it was a combination of the landing location site change and the inadequate software that caused the accident. Is that correct?
Yes, let me explain precisely. Yes, first of all, the landing site change, yes, impacted on this issue. Then for the software side parameter tuning issue, yes, technically we need to improve that point. However, the more important point is, we could not, realize like, the way to find out the issue in advance. I mean, before landing date. Then this is like almost our project management or program management issue. Then that means, as I mentioned in the improvement side, if we, determine the landing site earlier, we might be able to avoid this issue. Then technically, yes, software need to be improved. However, that issue comes from more program or project management side.
And lastly, how far away from your targeted landing site did the lander come down, and at what speed did it hit?
Okay, then first of all, far from means like horizontally or vertically?
Well, when it came down, where it landed, where it crashed, how far was that from where you had hoped to land? And at what speed did it impact the lunar surface?
Okay, then I think, the NASA LRO already took a picture of our, the most probable, the hard landing point. Then I think that point, I could not disclose the detailed number, but as you see in the picture in the presentation, I think, could you go to that slide? I think. Yeah, wait a moment. Yeah, this one. Yes, with this picture, I think you can estimate, how far from our target site. Again, for this, in this picture, I mean, center picture, this black circle is our target landing area. Of course, the center is our specific target site, but in reality, the most probable hard landing point is bit outside from our landing area. Then, yeah, I think you can, roughly estimate how far from our target and actual hard landing site. However, this deviation, I think is due to that, the bit inaccurate, estimation of the altitude and the velocity. Because again, due to the cratering, the estimated altitude and velocity were, incorrect. Then due to that, I don't think the lander correctly managed all trajectory and so on. And this, deviation, the deviation from target area was expected. Then for that touchdown speed side, yes, I think, it's bit correctly, the estimated speed. But by using our, the Doppler shift measurement of the communication, RF communication side, we estimated at the hard landing moment that speed could be more than 100 meters per second. Did I answer your question? Oh, sorry.
Yes. Yes, thank you very much. And so it's it's the steep crater rim that got you in the end. Is that what I'm understanding?
Yep. Yes.
Okay. Thank you very much.
Thank you very much.
Next question will go to Jeff Faust.
Hello, good evening, and thank you very much for this detailed explanation. Two quick questions. One, at approximately what altitude did the lander run out of propellant and begin that free fall to the surface? And then the second question is the software that was involved in, that's the sort of the root cause of this failure, was that developed by iSpace or provided by a partner for the mission? Thank you.
Okay, thank you for your question. Let me answer that, the question. Then, first of all, the altitude at the free fall timing. Yes, as I explained, when the estimated altitude is 0, the lander, the measured altitude was 5 kilometers. Then even after that, again, the lander kept descending. However, at that moment, the descending speed is really slow already. I mean, less than 1 meter per second. Then lander tried to, to keep that speed, for over 1 minute, but however, due to gravity, lunar gravity effect, finally we ran out the propellant. That means, even at free fall moment, the altitude is also around 5 kilometers. That is a question, the answer for first question. Then for the second question side, yes, first of all, let me clarify one point. This is the iSpace mission. Then iSpace is always responsible for any consequence at the end. Then, but for technical side, yes, we need to improve the software, onboard software. Then, as we developed this descent landing, the software together with REPA. But again, this comes from the iSpace side program or project management, the issue. Then we need to improve this point, and then we need to improve the software together with REPA.
Next question for Joey Roulette.
Hi, thanks. Joey Roulette with Reuters, and thank you for doing this detailed briefing. I just wanted to follow up real quick on Jeff's question. I know iSpace, takes largely responsibility for the outcome of this mission, but did Draper develop the landing software? Was it Draper that did that?
Okay. Yes, thank you for your question. Yes, basically, the Draper, developed our landing software. However, iSpace side, defined the requirement for that software and so on. Then here, due to the relationship, of course, if the iSpace failed in our project management, it could naturally flow down to the how can I say, insufficient, the landing software's parameter tuning and so on. Then, of course, in reality, yes, the Draper side is design and implementing that landing software. However, the issues comes from our side. I mean, the requirement, flow down, and project management, the product management.
Gotcha. Thanks. And I just had a few other quick questions to follow up on Marcia Dunn's question. What was your estimation for how far the crash site was from the targeted landing site? How many kilometers was that?
Okay, yeah. Of course, I know the number. Then if I can mention that number, yes, I can do that. But I'm sorry, I cannot disclose the quantitative, specific number. But I think you can estimate that the distance. I think from those the picture. Then I'm sorry, I cannot say that the really specific number. Yeah, I'm sorry.
Okay, no worries. And I know I think you don't know the insurance payment or what that will be, but what do you expect that insurance payment for Mission 1 to be?
Well, I'm going to answer that question. So this lunar insurance is designed and then provided by the Mitsui Sumitomo Insurance Company, and then this insurance will cover including the lunar landing. And then, as I said earlier, we are expecting to receive the payment, and then however, still it's under the confirmation by the Mitsui Sumitomo Insurance Company. That is the current situation.
Mm-hmm. Thanks. And last question, after looking at the data and kind of better understanding everything that went wrong, what changes are you planning for Mission 2? And while there's no significant cost increase, as you said, what will that cost increase be since understanding these issues from Mission 1?
Okay, I guess so. Yes, yeah, for that question, yes, as I mentioned, that improvement point, yes, we need to do some more fine parameter tuning, and then we also need to more, I would say, elaborate our test campaign to identify this type of issue in advance, then we need to such kind of improvement, but that impact is really minor. Then in addition, as I said, this is not hardware failure, then we don't need to modify the hardware side. Then, that means basically the impact could be, minor always. On the other hand, of course, we need to add more effort, on that, the improvement, of course. Then, but, I could not say the specific number, I'm sorry. But, the amount itself is really, really minor.
Thank you.
Thank you.
Next question will go to Tim Fernholz.
Hi there, Tim Fernholz from Quartz. Thank you for taking the time to speak with us today. Just a question of clarity. When you're talking about the estimated altitude produced by your software, is that from like dead reckoning and gyroscopes, or how do you determine that figure?
Okay, thank you for your question. Yes, yeah. First of all, this estimated altitude, estimated position, basically the propagation from IMU. The IMU always measured like acceleration of that lambda. Then based on that data, with high frequency, lambda always updated its own position. This called estimated altitude or estimated position. On the other hand, this measured altitude means measured data by laser rangefinder.
Great, thank you so much. That's very helpful. And I just wanted to follow up. I know the lunar insurance is maybe difficult to talk about, but it's very interesting because it's the first time. Can you speak to what maybe share of the mission cost that premium on that insurance was, or what share of the mission cost you hope it will cover, if you can't say specific, monetary figures?
Well, thank you for your question. I think everyone interested in that point. However, it's under the non-disclosure. So unfortunately, I cannot tell the detail. I'm sorry for that.
Thank you so much.
Next question will go to Kenneth Chang.
Oh, I was wondering, what was the original landing site? Was it not in a crater? And was the specifications for the landing software didn't include a specification to deal with this something like a crater rim? And I guess it's kind of surprising to me that any simulation of this landing site that you wouldn't have noticed this sudden jump in altitude from the crater rim.
Okay, yeah, let me answer that question. Yes, first of all, for the landing site, previous, I would say primary landing site. Yes, in my understanding, those landing sites are not inside the crater. Then, this primary landing site is, I think it's really unique. Then I think it's also beneficial too. But, that is, the reality. Then for the verification side, yes, again, we did a lot of simulation, like a Monte Carlo type of simulation, of course. Then but the point is here at the simulation, we always define the range of detailed lunar terrain simulation region. Of course, really under ideal condition, we can, all lunar terrain region, should be, simulated and then run simulation. However, it really cost means it really costs computational resources. Then in reality, it is impossible to run a bunch of simulation with such kind of setting. Then, we always need to limit the region to simulate the lunar terrain. Then, but in this case, with this landing site case, I would say that, the terrain simulation region, is not, I would say proper to capture this crater rim issue in advance. Of course, again, originally this the simulation range is based on the previous landing site. Then just in case for that landing site requirement or landing area requirement are compatible with the previous landing site. Then for the slope, border, the landing accuracy, and are compatible, between the current primary landing site and the previous the primary landing site. In that sense, we don't have any difference. However, the point is we need to consider the trajectory, and we also need to check, what kind of region the lander fly over. Then by considering such a condition, we should set proper simulation region and then capture this issue in advance.
Where was the previous landing site?
I think we used to announce in the press release that Lucas, I'm sorry, it's hard to pronounce for Japanese, Lucas Somniol. Then I think you can check the previous landing site in our website or somewhere. Then I'm sorry, I cannot properly, pronounce that site, sorry.
But that was a plane and not within a crater?
Yeah, it's not inside the crater. Yeah.
Okay, thank you.
Next question, back to Marcia Dunn.
Yes, hi. If you had not changed the landing location, do you think that this landing would have been successful since it would have been just flat?
Okay, yeah. Thank you for that question. Yes, I'm going to answer that question. Yes, of course, this is really hypothetical discussion. But yes, we might have a chance, to successfully land on the moon if we didn't change the landing site. But it is just like hypothesis. Then I could not say we surely land on the moon if we didn't change the landing site. But surely the situation should be different. Then it might positively impact on that the result. However, the point is through this the flight result we learned a lot of things, including this the crater rim, lunar surface topological or terrain, the impact on the overall mission zone. Then even this, I think the unsuccessful landing, we learned a lot of things from this experience.
Thank you.
Are there any more questions? If you could raise your hand, please. We'll go back to Joey Roulette.
Hey, thanks. I just wanted to be clear. I think you guys might have mentioned this before, but when was the decision made to change the landing site? Was that years prior in CDR, or was there a sooner date? Sorry for repeating the question. I just want to be clear.
Yeah, thank you for your question. Yes, then because my answer was really vague, then I might make you confused. I'm sorry. Then, but again, I could not say specific date. Changing the the landing site. But as we already made the announcement, we completed the CDR 2021 February. Then finally, we announced the current landing site 2022 November. Then between that long period, we made a decision to change the landing site. I'm sorry, I couldn't say when specifically when we changed, but between that duration, over that duration, we changed the landing site.
And I don't need a specific date, but can you say maybe like months before or I'm sorry, I guess I could go back too, but yeah.
No months before, of course, no months before. Then yeah, but I'm sorry, I could not say. It's, yeah, the time, specific timing. Yeah, I'm sorry.
Next question goes to Tim Fernholz.
Hello again. Forgive me for missing this earlier, but can you just say briefly why the landing target site was changed?
Okay. Yeah, then let me answer that question. Yes, thank you for your question. Then for that, the reason why we changed the landing site is to maximize the benefit of the mission. The benefit of mission means the benefit in the lander side and the benefit in the payload side too. Because, this is like, the payload transportation business, and then we would like to maximize the payload service on the lunar surface. Then due to this positive reason, we try to change that landing site. And then, we made a decision to change the landing site.
Next question goes to MJ Lee.
Hi, thank you. I'm sorry if this was mentioned before, but I want to ask, how confident is iSpace now, based on this analysis, of how confident are you about the next mission, basically, that it will kind of reach the very final level next time?
Okay. Yeah, thank you for your question. Then let me answer that question. Then yes, first of all, the most important the point in this the mission one result is, yes, we had a gap in the estimated altitude and measured altitude. However, lander guidance and control fully worked properly. I mean, guidance control mean the control means the lander itself control, like altitude control, speed control, based on the wrong estimated information. Also, then but we completed all sequence finally, and then we can also successfully cancel the speed, and then the lander itself reached at really slow speed finally. And then the other point is we didn't lose the communication until the end of mission. That means anything unexpected happen in our onboard computer, communication subsystem, and so on, then we kept the communicating with the lander, and the lander also maintain the proper communication, the proper processing, and so on. Then that means we already got full set of the data until the end of the mission. Then that was also really important outcome from this mission too. Then based on these data and lessons learned, we are confident in improving our missions. And then, of course, as I say, team itself, then through this, the challenge, I mean, our team was really also improved, then extended. And I think with this, the more, the extended performance, I believe we can, make a success in the next challenge.
Thank you.
Thank you. Thank you.
Joey, do you have another question?
Oh, no, I don't. Sorry, I'll lower my hand.
No problem. Thank you.
Thank you very much for your participation today. So as we explained, we have very clear result from the mission 1, and we are now ready to feedback what we learned from mission 1 to mission 2, mission 3, and then increase our maturity of our technology and then service. And then this is a really great first step. We are ahead of the this experience as a commercial company. And then we will moving forward for the second mission, third mission. Never quit the lunar quest. Thank you very much.
Thank you.
Recording stopped.